Welcome to Dr. Jed's continuing calculus series. This is section 4.6 from Rogowski. Graphing. Now it's called graphing, and it's some other title. I call it graphing with calculus because we're going to use what we've learned about the first derivative and the second derivative to actually make the graphs. The first thing is to find out what the steps are, and then to use examples to illustrate what we're going to do. So the steps, here are the steps. You can break it down into multiple steps if you want, but this is how I call it. The first step isn't always that interesting. What is the domain of f? Most of the time that's pretty obvious, it's pretty easy, and it's not usually relevant. But if you've got something like a natural log in your function, or a secant, it can be actually pretty relevant to figure that out just so you're prepared. Next, y-intercepts and x-intercepts. These are not really that critical to find, but they're easy. A y-intercept is just plug 0 into the function. That's almost always easy to do. An x-intercept, you solve for where the function is 0. It's a little harder, but it's usually pretty good. And it's a good thing to have because you know where you cross the x-axis. Then we're going to find horizontal asymptotes and vertical asymptotes. Horizontal asymptotes are what happen as you go to infinity or minus infinity. Or is it infinity and minus infinity? Anyway, to each side. Sometimes it's the same, sometimes it's different. And then vertical asymptotes are places, typically discontinuities in the domain, issues right here, and they're usually straight up and down. An asymptote is something you approach, so we'll get close to them, and that will help us with our graph. Then we get to the real calculus. First we find the first derivative, use it to find critical points, that's where the derivative is 0 or doesn't exist. Then make a number line, figure out where the function is increasing, where it's decreasing, and therefore what the local mins and maxes are. This was from a previous section, but we'll go one step further down because we'll find the y value because we're going to use it for our graph. Next, we do the second derivative and similar things. We find the inflection points, we make a number line, and we find out where the function's concave up and concave down. Sometimes we need a few more points just to put it all together, but often that's enough. With that, a little bit of reasoning, and we can get a good graph. So let's try one. Let's start with a polynomial. Polynomials are actually fairly straightforward. Notice the domain is everything. There's no problems anywhere. The y-intercept, plug 0 in. You get 0. X-intercepts, we solve where this is 0. You can factor an x squared out of this. And you get that x could be 0, or x could be 3/2. How about step 2? The horizontal asymptotes. Well, as x goes to infinity and minus infinity, any kind of function that has rational components, like polynomials like this, the only important component, if you're going to infinity or going to minus infinity, is the one with the highest power of x. So this over here, it's got a 3 there, but it's not important. If x is a billion, this is a billion squared, this is a billion cubed. It's really big. This one's not. It goes away. If x goes to infinity, we have infinity. If x goes to minus infinity, well, if x goes to minus infinity, we have minus, minus, minus. So we're going to have minus infinity. So we have 2 of them. As x goes to infinity, we have infinity. As x goes to minus infinity, we have minus infinity. It's important just to know that. It helps us when we graph. Vertical asymptotes. Getting my tongue tied there. Vertical asymptotes are places where we run aground, where we have problems with a specific value, and there are none. There's a lot of material in each of these graphs. I may be going fast. Hopefully you can pause if you need to. 3. 3 has to do with critical points. We need to find the derivative. The derivative is fortunately easy to do. We get 6x squared minus 6x. We need where that is 0 or doesn't exist. And again, we don't have any issues with existence. So it's just 0 for us. And hopefully you can see, you can factor in 6x out. X could be 0 or positive 1. Now, what do you do with that? We make a number line. What kind of number line? We're testing the derivative. We want to know, these are the critical points, but we want to know, Are they mins? Are they maxes? And things like that. So we want to know what the derivative is in each region. Plug minus 1 into this derivative. Well, actually, we could use right here. We care if it's plus or minus. Put a minus 1 in. You get minus, minus. Minus times minus is plus. Put a 0.5 in. You get plus, minus. Plus times minus is minus. Put a 2 in. You get plus, plus. Plus times plus is plus. So we have increasing, decreasing, increasing. What does that tell us? It tells us this is a local max, that this is a local min. But we want more than that. We want to know the point. Remember I said we'd also have to go farther and find the y. How do you find the y? You plug it into the original. X equals 0, plug that in, you get y equals 0. X equals 1, plug that in, y is minus 1. Now let's go further. Let's go to step 4. Step 4 is the second derivative. Take the first derivative and take its derivative. 12x minus 6. Now inflection points are where that changes concavity. But we really want specifically where this is 0, because that helps us make a number line. The number line lets us check concavity, and hopefully you can see by putting a 0 in here. Put a 0 in here, you get a minus. Put a 1 in here, you get plus. We have concave down, we have concave up. So this is an inflection point. So x equals 1/2. Y equals, plug it in, you get minus 1/2. That's an inflection point. So we have a few points, we have some limits, and let's put it together on the next board. We have two interesting points from the first bullet. These are intercepts. We have a min at, a max here. We have a local min here, and we have an inflection point there. How do we do all of this? Well, basically, we put these points on the graph and see what else we need. All of the x's are, well, they're less than 2. So when you graph this, that's probably the range we need. All the y's are between 1 and minus 1. So let's put them together. 0, 0. 3/2, 0. 1 minus 1. And 1/2 minus 1/2. Okay. This one's a local max, so the graph looks like that. This one's a local min, so the graph looks like this. This one's an inflection point, so it changes from concave down to concave up, right there. Furthermore, if you recall, the graph was increasing after this, so it's going to go up. How far up does it go? Well, that's a question. This one was decreasing here. How far down? This is where knowing where the limits are, the horizontal asymptotes, is useful. This was increasing, and the limit was infinity. So we can just draw it like that. This was decreasing, and the limit was minus infinity. There's our graph. Let's try one that's slightly harder. Now, I'm going to save some time. I've already calculated a lot of the steps. f of x is a quotient now, 2x minus 1 over x plus 2. It's a rational function. So, how do you do this? First of all, the domain. The issues with domain on a rational function are where the bottom is 0. So our domain is everything except minus 2. What about the y-intercept? Plug 0 in. Here, that's 0, that's 0. You get minus 1 over 2. Right there. X-intercept. To make a fraction 0, we make the top 0. There it is. Plug that in, you get x is 1/2. Now, horizontal and vertical asymptotes are more interesting for rational functions. The horizontal asymptotes, well, as x goes to infinity, only the top and bottom terms of the highest power of x make a difference. So we're interested in these. For the horizontal asymptote, we get 2x over x. The x's will cancel. We just get 2. For the vertical asymptotes, well, that's where the bottom is 0. So we get x is minus 2. Actually, these 4 pieces represent 4 directions on this. The top can be 0 for the x-intercepts. The bottom can be 0 for vertical asymptotes. The highest power terms give you the horizontal asymptote, and the lowest, the constant terms, give you the y-intercept. So these 4 come from those sort of 4 rectangular bits of that. All that notwithstanding, though, let's now take the derivative. Let's find the critical points. The derivative, quotient rule, gives us this. And the top of this is never 0. The bottom is 0 when x is minus 2, so we only have one critical point. Some people would say x is minus 2 is not a critical point because you can't even plug it into the function. It's not in the domain. I'm going to call it a critical point because it's critical to how the graph looks. Here's our derivative graph. You can take any value you want, but plug it into here. The top is 5, it's positive. The bottom is squared, it's positive. No matter where you go, you have positive over positive. This is a graph that is always increasing. Now you might think, well, if that's the case, then it's just going from minus infinity to positive infinity. But that's not the case. Remember, the horizontal asymptote is 2. It's going from 2 to 2. There's a lot of interesting things going on inside of there, but it's going from 2 to 2. Let's graph what we know. We know the y-intercept is minus 1/2. We know that x-intercept is positive 1/2. That's the only place it crosses the x-axis. The horizontal asymptote. An asymptote is drawn with dashed lines. It's something you approach, but you never actually reach. Well, you could cross it, but you're going to approach it as you go out towards infinity. Vertical ones, at minus 2. This one you really actually can't cross no matter what, because then your function would be poorly defined. What else do we know? Well, that's it as far as values. How many regions does this make? Well, it looks like it makes 4, but horizontal asymptotes don't divide regions. So we actually have one region here, one region over here. And knowing something about it, we know it's always increasing in that region. So it's going like this. Well, how far is it going up? It goes up, and it approaches the horizontal asymptote. Could it cross the asymptote? The answer actually is yes, it could. It doesn't. Why? Because if it went over it, it would have to come back down. Coming down. What does coming down mean? It means the slope would be negative. Is the slope ever negative? The answer is no. If it went up and down, we'd have a negative slope at some point, and we don't. So it doesn't do that. How about over here? When you approach the asymptote, you either go to the top part or go to the bottom part. There's a couple pieces of logic here. First of all, it's always increasing, so that means it has to do this. It couldn't do the other, because then it would have been coming down. Or you could just reason, if it did that, it would cross the x-axis again. It never does. So it can't do that. That's one half. What about this half? We have no points at all. That's kind of problematic. It's tricky to draw a graph without points. But we know it starts at this horizontal asymptote here, and it ends either here or down here. It never crosses here, so it's not going to do that, and it's always going up. So even without any points, I can draw the graph. I know there's a lot of material in this section. Drawing graphs is tricky. Practice is the only answer. So try several of these, and we'll talk about them in class. Until next time, this is Dr. J.